Welcome to Advanced Linear Algebra. Today, we are going to explore a fascinating topic: minimal solutions to linear equations. Imagine you are standing in a vast, flat field and you need to walk to a long, straight fence. There are infinitely many points on that fence you could walk to, but you want to walk the shortest possible distance. In mathematics, we often face a similar scenario where a problem has infinitely many valid answers, and we need to find the most efficient one. Let us dive in and see how linear algebra helps us find this perfect shortest path. Now that we have our analogy of the fence, let us look at the mathematical equivalent. In linear algebra, we frequently encounter what we call an underdetermined system. This happens when we have more unknown variables than we have equations to solve them. Because there is simply not enough information to lock down a single unique answer, these systems generate infinitely many valid solutions. It is exactly like having infinite points on that fence. Any of those points will technically solve our equation, but out of all these infinite possibilities, we usually want to find one specific solution that is the smallest or most efficient. Building on the idea of finding the most efficient answer, we need a way to measure the size of our solutions. We measure this size using a concept called a norm, which is simply the mathematical term for the length or distance of a vector from the origin or the 0 point. The minimal solution is the specific vector that satisfies all the equations while having the absolute smallest possible norm. To keep our solution as short as possible, it must have absolutely no parts pointing in the direction of the null space. This means our minimal solution must be perfectly perpendicular, striking at a 90-degree angle to the entire null space. Knowing that our solution must be perpendicular to the null space leads us directly to this powerful equation. This is the master formula for the minimal solution. Let us break down what each piece means. The symbol S represents our desired minimal solution vector, which is the shortest possible path. A star is the adjoint matrix, which is essentially the transpose of our original matrix, and it ensures our solution is in that perpendicular space. The vector B is our target output. If you increase the values in the target vector B, the minimal solution S will scale up proportionally, meaning the distance grows. If the original matrix changes, the geometry of the solution space shifts, and this formula automatically recalculates the new shortest path. Before we move on to more complex systems, let us see this formula in action with a concrete example. Suppose we have a very simple problem, a single equation with two variables, x plus 2y equals 5. Because we have two variables but only one equation, this is an underdetermined system with infinitely many solutions. We want to find the minimal solution, the specific pair of x and y that satisfies the equation while being closest to the origin. First, we extract the coefficients of our variables to form the matrix A, which is just one row with the numbers 1 and 2. Next, we define a target vector B, which is simply the number 5 from the right side of our equation. Continuing with our calculation, we need to find the pieces for our master formula. We find the adjoint of A by taking its transpose. We take our single row and flip it into a single column vector with entries 1 and 2. This column represents the direction that is perfectly perpendicular to the null space. Next, we multiply the original matrix A by its adjoint. This is a simple dot product of the row with the column, which gives us the scalar number 5. Finally, we need the inverse of the matrix we just calculated. Since our matrix is just the number 5, its inverse is simply its reciprocal, which is the fraction 1/5. Now we have all the pieces to find our final answer. We calculate our intermediate value u by multiplying the inverse we just found, 1/5, by our target vector, 5. This gives us exactly 1. Finally, we multiply the adjoint matrix by this intermediate value to get the minimal solution S. The result is the vector with x equals 1 and y equals 2. If we check this, 1 plus 2 times 2 equals 5, so it perfectly solves the equation. Its length is the square root of 5, which is smaller than any other possible solution. We have successfully found the shortest path. To truly understand what we just calculated, let us look at this visually. Here we see a graph with an x-axis and a y-axis. The long diagonal line represents our equation, x plus 2y equals 5. Every single point on this line is a valid solution to our equation. Notice the arrow pointing from the origin to the point 1, 2. This is our minimal solution. See how it strikes the line at a perfect 90-degree angle? Because it is perpendicular, it is geometrically the shortest possible distance from the origin to the line. The other arrow pointing to 5, 0 is an alternative solution, but it is clearly much longer. This visually proves our mathematical derivation. Now that we have seen a simple case, let us try a slightly harder problem with 3 variables and 2 equations. Suppose we have the system x1 plus x2 plus x3 equals 3 and x1 minus x2 equals 0. We have 3 unknowns but only 2 equations. So this is again an underdetermined system with infinite solutions. We want to find the specific values that satisfy both equations simultaneously while keeping the overall vector length as small as possible. We build our matrix A by taking the coefficients from our 2 equations. Notice the 0 in the second row because there is no x3 term. We also build our target vector B using the numbers 3 and 0 from the right side. Following the same process as before, we find the adjoint A star by transposing the matrix A. The rows of A become the columns of A star. Next, we multiply A by A star. For the top left entry, we multiply the first row by the first column, giving us 1 plus 1 plus 1, which is 3. For the bottom right entry, we multiply the second row by the second column, giving us 1 plus 1 plus 0, which is 2. The off-diagonal entries become 0. This gives us a nice, clean diagonal matrix with 3 and 2 on the main diagonal. Moving forward, we need the inverse of the matrix we just calculated. Because our matrix A star is diagonal, finding its inverse is incredibly easy. We simply take the reciprocal of the numbers on the main diagonal. The 3 becomes 1/3 and the 2 becomes 1/2. Now we calculate our intermediate vector u by multiplying our inverse matrix by the target vector b, which contains 3 and 0. Multiplying the top row by the column gives 1/3 by 3, which is 1. Multiplying the bottom row gives 0. So our vector u is simply 1 and 0. For our final step, we multiply the adjoint matrix A star by our vector u to find the minimal solution S. When we perform this matrix multiplication, the result is a vector where x1 is 1, x2 is 1, and x3 is 1. Let us verify this physically. 1 plus 1 plus 1 equals 3, so the first equation works. 1 minus 1 equals 0, so the second equation works. Out of all the infinite ways to solve those two equations in three-dimensional space, the vector 1, 1, 1 is the absolute closest to the origin. Now that we have used this formula successfully twice, let us understand where it comes from. We are setting out to derive the master formula. We know from our earlier concepts that to be as short as possible, the minimal solution must be perfectly perpendicular to the null space. A fundamental theorem tells us that this perpendicular space is exactly the range of the adjoint matrix, A star. Because our minimal solution S must live in this perpendicular space, it must be the output of the adjoint matrix for some unknown input vector u. We write this as S equals A star times u. To force this to actually solve our system, we take our original equation and replace the unknown x with our special minimal vector, giving us A times A star u equals b. Continuing our derivation, we need to solve for that unknown vector u. By grouping A and A star together, we create a new, smaller square matrix. As long as our original equations were not redundant, this new square matrix will be invertible. To find our unknown vector u, we simply multiply both sides by the inverse of this new matrix. This gives us the exact value of the intermediate vector u. Now that we know what u is, we can plug it back into our very first assumption, where S equals A star times u. This substitution yields our final result, the beautiful master formula for the minimal solution. We have mathematically proven why this formula works. This mathematical derivation we just completed brings us to an important question. Why does this matter in the real world? Minimal solutions are actually the backbone of many modern technologies, especially in fields like machine learning, robotics, and control systems. Imagine a robotic arm that has 7 joints but only needs to move its hand to a specific three-dimensional coordinate. There are infinite ways it could bend its arm to get there. The minimal solution tells the robot how to reach the target while moving its joints the absolute least amount possible. This saves electricity and reduces wear and tear. Furthermore, in physics, nature almost always prefers the state of lowest energy. The smallest vector mathematically represents this lowest energy expenditure. We have covered a lot of ground today, so let us reinforce the most important ideas. First, remember that when a system of linear equations has more unknowns than constraints, it produces an infinite landscape of valid solutions. Second, by leveraging the adjoint matrix and the concept of orthogonal spaces, we can slice through this infinite set to find the single, unique solution that is closest to the origin. Finally, the master formula we derived acts as a mathematical compass, always pointing us to the most efficient, lowest energy answer available. You now have a deep understanding of minimal solutions. Great job working through these concepts.